I'm an astroseismologist using NASA's Kepler spacecraft to study the vibrations of stars to see what they're doing on the inside. Kepler is a spacecraft that's not orbiting the Earth. It's out in space orbiting the sun. That way it can point anywhere it wants in the sky, and it can just stare at that same position. There's no daytime, no nighttime, no clouds, and it just takes picture after picture after picture, so it actually sees several million stars at a time. But that's more data than it can actually transmit back to Earth. And so it works for a month at a time, and then at the end of a month, it turns to the Earth, transmits that data for one day, and then it turns back to the field and starts working again. So people like myself have to apply for targets that are interesting, and a board of astronomers read our applications and they come up with a list of targets that Kepler will observe. Vibrations of stars has really advanced a lot just using this data because we've never had data like this before. If you observe from the Earth, you have 7 or 8 hours of nighttime, and then you have 12 hours of daytime when you can't get data. Kepler observes all the time, and that has completely changed the field of astroseismology. Well, I'm an observer, and I work with the data. We also have theorists, and the theorists make models. They predict what the pulsations should be. So we look at the data, and we see what the pulsations actually are, and by looking at the difference between what the star is doing and what the model thinks it should be doing, we can figure out where the model's correct and where the model is incorrect, and we can put in new physics, new conditions that then tell us more about the insides of these stars. Well, at Missouri State, we emphasize undergraduate education, and part of that undergraduate education is giving them research experience to see if this field is interesting to them as a profession. A lot of our grant money is spent on hiring students to come in here and actually be research interns. And so we work together to determine what the star is actually doing based on what we see in the data. And typically they see these discoveries before I do. These stars are extremely hot, so they behave somewhat differently than even stars like our sun do. On the inside, some heavy things like iron and nickel float, and some light things like helium actually sink under the gravity. Well, we found that one of our stars wasn't spinning at the same speed on the outside as it was on the inside, and it was predicted that just like when an ice skater pulls in her arms and she spins much faster, that as these cores contracted as they aged, the core would be spinning much faster. And we discovered a star where the core is actually spinning 3 times slower than the outside. And in many of the cases, our stars are in binaries, that is, they have a companion. When stars get into these close binaries, they're locked, so one side is always facing the other star. And what we have found is that is not the case in these stars. The entire year lasts half of our day, so they spin around each other twice per day, but their spin of the star is actually 20 to 50 days. So they're spinning much, much slower than they orbit each other, which is completely surprising.